Imagine this. You're racing through space at 99% the speed of light, watching the universe transform around you. Stars streak past like cosmic fireworks, and something incredible happens. Time itself begins to crawl. What takes hours for you feels like minutes. What seems like days to outside observers passes as mere hours in your reference frame. Today we're diving deep into why time slows down as you approach light speed, and trust me, the answer will change how you see reality forever. Are you ready? Let's begin. The story begins with Albert Einstein, a patent clerk who revolutionized our understanding of reality in 1905. His special theory of relativity revealed that time isn't the constant, unchanging river we thought it was. Instead, time is elastic, stretching and compressing based on how fast you're moving. This discovery shattered our intuitive understanding of the universe and opened doors to possibilities that still boggle the mind today. But Einstein didn't just theorize about time dilation, he proved it mathematically. The Lorentz factor, named after Dutch physicist Hendrik Lorentz, shows us exactly how time stretches as velocity increases. At everyday speeds, this effect is negligible. When you're driving down the highway at 70 kilometers per hour, you age about 1 nanosecond less per hour than someone standing still. But as you approach the speed of light, something extraordinary happens. At 50% light speed, time slows down by about 15%. At 90%, it slows by more than half. At 99%, time crawls at just 14% of its normal rate. And here's the kicker. At exactly the speed of light, time would theoretically stop completely. But here's the catch. Nothing with mass can actually reach light speed. Only massless particles like photons can travel at this cosmic speed limit. The mathematics behind this phenomenon is both elegant and profound. As your velocity approaches light speed, the Lorentz factor approaches infinity. This means that from the perspective of a stationary observer, your clocks would appear to tick slower and slower until they nearly freeze. But from your perspective, time feels completely normal. You don't feel like you're moving in slow motion. The universe around you appears to speed up instead. This isn't just theoretical anymore. We've measured time dilation in countless experiments. Atomic clocks flown on airplanes show measurable time differences compared to identical clocks left on the ground. The Global Positioning System satellites orbiting Earth experience time dilation effects that engineers must account for, or your GPS would be off by kilometers within hours. Particle accelerators routinely observe subatomic particles living longer than they should because they're moving at near-light speeds. The most dramatic example comes from cosmic ray muons. These particles are created when cosmic rays slam into Earth's atmosphere about 10 kilometers up. Muons normally decay in just 2 microseconds, far too short to reach the ground. But because they're traveling at 99.8% the speed of light, time dilation extends their lifetimes by a factor of 15. What should be a 2 microsecond journey becomes a 30 microsecond adventure, allowing these cosmic messengers to rain down on us. But why does this happen? The answer lies in the fundamental structure of spacetime itself. Einstein realized that space and time aren't separate entities. They're woven together into a 4-dimensional fabric called spacetime. When you move through space, you're also moving through time, and there's a cosmic speed limit that governs both. The faster you move through space, the slower you move through time, and vice versa. If this cosmic dance of space and time has captured your imagination, don't forget to subscribe and ring that notification bell. Your support helps me continue exploring these incredible mysteries that connect us all to the cosmos. Together, we're uncovering the secrets of a universe that's far stranger and more beautiful than we ever imagined. Think of it like this. Imagine you're walking across a field and you can choose to walk north, east, or any combination of the two. If you walk purely north, you're not moving east at all. If you walk northeast, you're moving slower in the north direction than if you went straight north. Space-time works similarly. You're always moving through space-time at the speed of light, but you can distribute that motion between space and time. The more you move through space, the less you move through time. This revelation connects to something even more profound about our cosmic story. Every atom in your body was forged in the heart of a dying star billions of years ago. When those stars exploded as supernovae, they scattered their stellar ashes across the galaxy at significant fractions of light speed. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of it experienced time dilation during its cosmic journey to eventually become part of you. The implications stretch far beyond physics textbooks. Time dilation affects everything from the GPS in your phone to our understanding of the universe's age. When we observe distant galaxies through powerful telescopes like the James Webb Space Telescope, we're seeing them as they existed billions of years ago. The light from these ancient galaxies has been traveling through space for so long that we're literally looking back in time, witnessing the universe's childhood. But here's where it gets even more mind-bending. From the perspective of a photon of light traveling from a distant galaxy to your eye, the journey is instantaneous. Due to extreme time dilation at light speed, no time passes at all for the photon. It experiences the entire 13.8 billion-year journey as a single moment. In a very real sense, that ancient starlight touching your retina right now exists in a timeless state, connecting you directly to the cosmic past. This timeless nature of light reveals something profound about the universe's interconnectedness. When you look up at the night sky, you're not just seeing distant suns, you're witnessing a cosmic timeline stretching back billions of years. The light from Proxima Centauri, our nearest stellar neighbor, left that star 4.24 years ago. The glow from the Andromeda Galaxy began its journey when early humans were just learning to use tools 2.5 million years ago. You're literally seeing the universe's history written in starlight. But time dilation creates paradoxes that challenge our everyday understanding of reality. Consider the famous twin paradox. One twin travels to a distant star at near light speed while the other stays on Earth. When the traveling twin returns, they've aged much less than their Earth-bound sibling. This isn't just theoretical, it's been confirmed with atomic clocks on airplanes and even with particles in accelerators. Time truly is relative, and motion through space determines how quickly you move through time. The practical implications of time dilation extend far beyond thought experiments. NASA's Parker Solar Probe, launched in 2018, reaches speeds of over 400,000 kilometers per hour as it dives toward the Sun. While this seems incredibly fast, it's still only about 0.06% of light speed. Even at these record-breaking velocities, time dilation effects are measurable but tiny, just a few nanoseconds over the mission's lifetime. But imagine if we could build spacecraft capable of reaching significant fractions of light speed. A journey to Proxima Centauri at 90% light speed would take about 4.7 years from Earth's perspective, but only about 2 years for the travelers due to time dilation. The crew would arrive younger than they would have if they'd stayed home. However, the challenges of traveling at such speeds are immense, and if you're curious about the devastating effects that near light speed travel would have on the human body, check out my video called Why Light Speed Would Destroy Us Before We Even Arrive, where I explore the deadly physics that make such journeys nearly impossible. The link is in the description and pinned on the comments. The relationship between velocity and time dilation follows a precise mathematical curve. At 10% light speed, time slows by just 0.5%. At 50%, it slows by about 13%, but as you push toward 90% light speed and beyond, the effects become dramatic. At 99%, time crawls at just 14% of normal speed. At 99.9%, it's down to 4.5%. The curve becomes steeper and steeper, approaching infinity as you near light speed. This mathematical relationship reveals why light speed is truly a cosmic speed limit. As you approach it, time dilation becomes so extreme that reaching exactly light speed would require infinite energy and result in time stopping completely. It's as if the universe has built-in protection against causality violations. If you could exceed light speed, you could theoretically travel backward in time, creating paradoxes that would tear apart the logical structure of reality. The discovery of time dilation revolutionized our understanding of simultaneity, the idea that events can happen at the same time. Einstein showed that simultaneity is relative. Two events that appear simultaneous to one observer might occur at different times for another observer moving at high speed. This means there's no universal now that applies everywhere in the universe. Your present moment is different from the present moment of someone moving relative to you. This relativity of simultaneity has profound implications for our understanding of free will and determinism. If there's no universal present moment, then the future and past might be equally real. Some physicists interpret this as evidence for a block universe, where all of time exists simultaneously, and our perception of flowing time is just an illusion. Others argue that quantum mechanics preserves genuine randomness and choice within the constraints of relativity. The cosmic microwave background radiation, the afterglow of the Big Bang, provides a natural laboratory for studying time dilation on cosmic scales. This ancient light has been traveling for 13.8 billion years, and its properties tell us about the universe's expansion history. As space itself expands, it stretches the wavelengths of this primordial light, creating a form of cosmological redshift that's related to time dilation effects. Gravitational time dilation adds another layer to this cosmic story. Einstein's general theory of relativity, published in 1915, revealed that gravity also affects the flow of time. Clocks run slower in stronger gravitational fields. This means time passes slightly slower at sea level than on a mountaintop, and much slower near massive objects like black holes. The GPS satellites orbiting Earth experience both velocity-based time dilation and gravitational time dilation, and engineers must account for both effects. The most extreme example of gravitational time dilation occurs near black holes. As you approach the event horizon of a black hole, time dilation becomes infinite from the perspective of a distant observer. If you watch someone fall into a black hole, you'd see them slow down and freeze at the horizon, their image growing redder and dimmer until it fades away. But from the falling person's perspective, they pass through the horizon normally, experiencing no unusual passage of time. This connection between motion, gravity, and time reveals the deep unity underlying Einstein's theories. Both special and general relativity show that time is not the absolute universal constant that Newton imagined. Instead, time is dynamic, flexible, and intimately connected to the structure of space and the distribution of matter and energy. We live in a universe where time itself is part of the cosmic dance. The study of time dilation has led to practical technologies that affect your daily life. Particle accelerators like the Large Hadron Collider routinely accelerate particles to 99.9999% of light speed. At these velocities, particles that normally decay in microseconds can survive for much longer due to time dilation, allowing scientists to study them in detail. These experiments have confirmed Einstein's predictions to extraordinary precision. Modern atomic clocks are so precise that they can detect time dilation effects from walking up a flight of stairs. The National Institute of Standards and Technology has atomic clocks that would lose less than 1 second over the age of the universe. These incredibly precise timepieces have revealed time dilation effects from elevation changes of just a few feet, confirming that time truly runs slower in stronger gravitational fields. The precision of modern atomic clocks has opened new frontiers in testing Einstein's theories. In 2010, scientists at the National Institute of Standards and Technology demonstrated that they could measure gravitational time dilation by raising one atomic clock just 33 centimeters above another. The higher clock ran faster by about 4 parts in 10 to the 17th, a difference so tiny it would amount to less than 1 second over the entire age of the universe, yet still measurable with today's technology. These ultra-precise measurements aren't just academic exercises, they're helping us understand fundamental questions about the nature of reality itself. Some theories propose that the constants of physics might change over cosmic time. By comparing atomic clocks based on different physical processes, scientists can search for evidence of such changes. So far, the constants appear remarkably stable, but the search continues with ever-increasing precision. The Global Positioning System provides perhaps the most practical demonstration of time dilation in everyday life. GPS satellites orbit Earth at about 14,000 kilometers per hour and experience weaker gravity than we do on the surface. Both effects cause their onboard atomic clocks to run fast compared to Earth-based clocks, about 38 microseconds per day faster due to gravitational effects, minus 7 microseconds per day due to velocity effects, for a net gain of 31 microseconds daily. This might seem insignificant, but GPS works by measuring the time it takes radio signals to travel from satellites to your receiver. Light travels about 30 centimeters in 1 nanosecond, so a timing error of 31 microseconds would cause position errors of about 9 kilometers. Without relativistic corrections, GPS would be useless for navigation within hours of activation. Every time you use GPS, you're relying on Einstein's theories of relativity. The story of GPS and relativity illustrates how fundamental physics discoveries eventually transform everyday life. When Einstein published his theories in the early 20th century, they seemed like abstract mathematical curiosities with no practical applications. Who could have predicted that understanding time dilation would become essential for navigation systems that billions of people use daily? This reminds us that today's most esoteric physics research might power tomorrow's revolutionary technologies. Time dilation also plays a crucial role in our understanding of stellar evolution and cosmic distances. When we observe distant supernovae, we see them evolving in slow motion due to cosmological time dilation. A supernova that takes 30 days to fade in its rest frame appears to take longer when observed from Earth if it's at high redshift. This effect must be accounted for when using supernovae as standard candles to measure cosmic distances and study dark energy. The Hubble Space Telescope and other observatories have detected supernovae so distant that their light has been traveling for over 10 billion years. These ancient explosions appear stretched in time, taking longer to brighten and fade than identical nearby supernova. This time dilation effect provided some of the first evidence that the universe's expansion is accelerating, leading to the discovery of dark energy and the 2011 Nobel Prize in Physics. Particle physics experiments routinely exploit time dilation to study unstable particles. Muons created in cosmic ray showers high in the atmosphere normally decay in about 2 microseconds. At rest, they couldn't travel more than 600 meters before decaying, but cosmic ray muons travel at speeds close to light, experiencing significant time dilation. From our perspective, their lifetimes are extended by factors of 10 or more, allowing them to reach Earth's surface and rain down on us constantly. The study of cosmic ray muons led to one of the first confirmations of special relativity. In 1941, Bruno Rossi and David Hall measured the number of muons at different altitudes on Mount Washington. They found that far more muons reached sea level than could be explained without time dilation. This experiment provided compelling evidence that time really does slow down for fast-moving objects, just as Einstein predicted. Neutrinos, those ghostly particles that barely interact with matter, provide another window into time dilation effects. When supernova 1987A exploded in the Large Magellanic Cloud, neutrino detectors on Earth recorded the arrival of neutrinos from the explosion. These neutrinos had traveled 160,000 light-years through space, and their arrival times were consistent with them traveling at very close to light speed, experiencing minimal time dilation due to their tiny but non-zero mass. The detection of neutrinos from SN 1987A marked the birth of neutrino astronomy and provided a unique test of relativity over cosmic distances. The fact that neutrinos and light from the supernova arrived within hours of each other after traveling for 160,000 years confirmed that both travel at essentially the same speed through the vacuum of space, validating Einstein's theories on galactic scales. Modern neutrino experiments continue to probe the relationship between mass, velocity, and time. The discovery that neutrinos have mass, confirmed by experiments like Super Kamiokande in Japan, means they must travel slightly slower than light and experience time dilation. These effects are incredibly tiny because neutrino masses are so small, but they're measurable with sufficiently sensitive experiments. The Large Hadron Collider at CERN accelerates protons to 99.9999% of light speed, creating conditions where time dilation effects are extreme. Particles that would normally decay in tiny fractions of a second can survive long enough to travel around the 27-kilometer ring multiple times before decaying. This allows physicists to study exotic particles and fundamental forces under conditions that existed only in the first moments after the Big Bang. When protons collide at these incredible energies, they create showers of new particles, many of which are highly unstable. Time dilation extends the lifetimes of these particles just enough for sophisticated detectors to measure their properties before they decay. Without time dilation, many of the discoveries made at the LHC would be impossible because the particles would decay before traveling far enough to be detected. The relationship between energy, mass, and time dilation reveals deep connections in physics. Einstein's famous equation E equals mc squared shows that mass and energy are interchangeable. As particles are accelerated to higher speeds, their kinetic energy increases dramatically, and this energy contributes to their effective mass. The more massive a particle becomes, the more energy is required to accelerate it further, creating a natural barrier at light speed. This energy-mass relationship creates a fascinating feedback loop in particle accelerators. As particles approach light speed, they become effectively more massive, requiring exponentially more energy for each additional increment of velocity. The Large Hadron Collider consumes about 120 megawatts of power, enough to supply a small city just to maintain the energy needed to keep protons circulating at near-light speeds. Yet despite this enormous energy input, the protons never quite reach light speed, always falling just short of that ultimate cosmic barrier. The concept of relativistic mass helps explain why nothing with rest mass can reach light speed. As velocity approaches the speed of light, the energy required to accelerate further approaches infinity. It would take all the energy in the universe to push even a single electron to exactly light speed. This isn't a limitation of our technology, it's a fundamental feature of spacetime itself. The universe has built-in protection against causality violations. Time dilation effects become particularly dramatic in the realm of black holes, where gravity warps spacetime to extreme degrees. Near the event horizon of a stellar mass black hole, gravitational time dilation can slow time by factors of thousands or millions. An astronaut falling toward a black hole would experience time normally from their perspective, but outside observers would see them slow down dramatically as they approach the point of no return. The event horizon. Telescope's historic image of the black hole in galaxy M87, released in 2019, captured light from matter spiraling around the event horizon at significant fractions of light speed. This superheated plasma experiences both velocity-based and gravitational time dilation. From our perspective, 13 billion light-years away, we're seeing this cosmic dance playing out in extreme slow motion due to these relativistic effects. Gravitational waves, ripples in spacetime itself, travel at exactly the speed of light and provide another laboratory for studying time dilation. When the Laser Interferometer Gravitational Wave Observatory detected its first gravitational wave signal in 2015, it observed the final moments of two black holes spiraling into each other. As these massive objects accelerated to significant fractions of light speed in their death spiral, time dilation effects became extreme. The LIGO detection revealed black holes with masses 30 times greater than our Sun, spinning around each other at speeds approaching light speed before merging. In the final milliseconds before collision, these black holes were experiencing time dilation factors of hundreds or thousands. The gravitational waves they produced carry information about these extreme time dilation effects, encoded in the frequency and amplitude of the space-time ripples. Binary pulsar systems provide natural laboratories for testing time dilation over decades of observation. The Hulse-Taylor binary pulsar, discovered in 1974, consists of two neutron stars orbiting each other every 7.75 hours. As they spiral inward due to energy loss from gravitational wave emission, their orbital velocity increases and time dilation effects become more pronounced. Observations of the Hulse-Taylor pulsar over more than 40 years have confirmed Einstein's predictions with extraordinary precision. The system is losing energy at exactly the rate predicted by general relativity, and the time dilation effects match theoretical calculations to better than 1 part in 10,000. This system earned Russell Hulse and Joseph Taylor the 1993 Nobel Prize in Physics for providing the first indirect evidence of gravitational waves. The study of pulsars has revealed time dilation effects throughout our galaxy. These rapidly spinning neutron stars emit beams of radio waves like cosmic lighthouses, and their rotation periods are incredibly stable, more precise than the best atomic clocks. When pulsars are part of binary systems, their orbital motion creates periodic Doppler shifts and time dilation effects that astronomers can measure with exquisite precision. Some millisecond pulsars rotate hundreds of times per second, with surface velocities reaching significant fractions of light speed. The matter at the equator of these ultra-fast spinners experiences measurable time dilation compared to matter at the poles. This creates subtle effects in the pulsar's emission that astronomers can detect, providing insights into the extreme physics of neutron star interiors. The cosmic microwave background radiation, the afterglow of the Big Bang, preserves information about time dilation effects from the early universe. As this ancient light has traveled for 13.8 billion years, it has been stretched by the expansion of space itself. This cosmological redshift is related to time dilation. Distant galaxies appear to be moving away from us, and their light is time dilated just as if they were moving at high speeds through space. The Planck satellite, which operated from 2009 to 2013, mapped the cosmic microwave background with unprecedented precision. The tiny temperature fluctuations in this ancient light encode information about the universe's composition, age, and expansion history. These measurements rely on understanding how time dilation and redshift affect the propagation of light across cosmic distances. Dark energy, the mysterious force accelerating the universe's expansion, creates time dilation effects on cosmic scales. As space expands, distant galaxies recede from us at ever-increasing speeds. The most distant observable galaxies are receding at speeds approaching light speed due to the expansion of space itself. This creates extreme cosmological time dilation. We see these ancient galaxies evolving in extreme slow motion. The James Webb Space Telescope, launched in 2021, is designed to observe galaxies so distant that their light has been traveling for over 13 billion years. These primordial galaxies appear highly redshifted and time-dilated. What might have been rapid star formation and galactic evolution in their rest frames appears stretched out over millions of years from our perspective due to cosmological time dilation. Future space missions will push our understanding of time dilation to new extremes. The proposed Breakthrough Starshot project aims to send tiny spacecraft to Proxima Centauri using powerful lasers to accelerate light sails to 20% of light speed. At such velocities, time dilation effects would be noticeable. The journey would take about 20 years from Earth's perspective, but slightly less from the spacecraft's perspective. Even more ambitious concepts involve generation ships traveling at significant fractions of light speed to nearby star systems. Crew members on such vessels would experience time dilation effects that could amount to years or decades over the course of an interstellar journey. They would arrive at their destination younger than they would have if they had remained on Earth, having literally traveled into the future through the effects of time dilation. The philosophical implications of time dilation challenge our most basic assumptions about reality. If time is relative and depends on motion and gravity, what does this mean for our understanding of existence itself? Some physicists and philosophers argue that time dilation reveals the illusory nature of our perception of time. What we experience as the flow of time might be nothing more than our limited perspective on a four-dimensional reality where past, present, and future all exist simultaneously. This block universe interpretation suggests that your birth, your current moment reading these words, and your eventual death all exist equally in the fabric of space-time. Time dilation doesn't change the events themselves, it only changes how different observers experience the intervals between events. From this perspective, time travel isn't about changing the past or future, but about taking different paths through the fixed landscape of space-time. Yet quantum mechanics introduces uncertainty into this seemingly deterministic picture. The quantum world is fundamentally probabilistic, with particles existing in superpositions of multiple states until measured. Some interpretations of quantum mechanics suggest that the future isn't fixed, but emerges from quantum possibilities. Time dilation might affect how these quantum possibilities collapse into definite outcomes, creating a complex interplay between relativity and quantum mechanics. The search for a theory of quantum gravity, a framework that unifies Einstein's relativity with quantum mechanics, might revolutionize our understanding of time dilation. At the smallest scales, near the Planck length of 10 to the negative 35 meters, space-time itself might become quantized. Time might not be continuous but made up of discrete units like frames in a cosmic movie. Such a discovery would fundamentally change how we understand time dilation effects. String theory, one candidate for quantum gravity, suggests that our familiar three dimensions of space and one dimension of time might be embedded in a higher dimensional reality. In this framework, time dilation might be a consequence of how matter and energy move through these extra dimensions. While string theory remains highly speculative, it offers tantalizing possibilities for understanding the deepest nature of time and space. The study of time dilation has practical implications for the future of human space exploration. As we venture farther from Earth, time dilation effects will become increasingly important for mission planning. A journey to Mars involves minimal time dilation, but trips to the outer solar system or nearby stars would require careful consideration of relativistic effects on crew aging, equipment degradation, and communication with Earth. Imagine a future where humans regularly travel between star systems at significant fractions of light speed. Families would be separated not just by distance, but by time itself. A parent leaving for a 20-year journey to Alpha Centauri at 90% light speed would return to find their children aged 20 years while they had aged only about 9 years. These time dilation effects would create new forms of social and psychological challenges for spacefaring civilizations. The biological implications of time dilation remain largely unexplored. While we understand the physics of how time slows down at high speeds, we don't fully understand how this might affect biological processes. Would cellular aging slow down proportionally with time dilation? Would DNA repair mechanisms work differently in a time-dilated reference frame? These questions will become crucial as we develop technologies for high-speed space travel. Medical research in space has already revealed how microgravity affects human physiology, but the effects of extreme time dilation remain theoretical. Some scientists speculate that time dilation might actually be beneficial for long-duration space travel, effectively extending human lifespans relative to Earth-based observers. Astronauts on high-speed interstellar missions might age more slowly, allowing them to survive journeys that would otherwise exceed human lifespans. The concept of time dilation has inspired countless works of science fiction, from novels to movies to television shows. These stories often explore the human drama of time dilation, the emotional cost of leaving loved ones behind, the challenge of maintaining relationships across time-dilated distances, and the philosophical questions about identity and continuity when time itself becomes relative. Yet science fiction often misrepresents the realities of time dilation. Many stories depict time dilation as something that can be turned on and off at will, or as a way to travel backward in time. In reality, time dilation is an inevitable consequence of motion and gravity. You can't escape it or control it. You can only choose how to move through space-time and accept the temporal consequences of your choices. The measurement of time dilation has driven the development of increasingly precise timekeeping technologies. Atomic clocks, which use the vibrations of atoms as their timekeeping mechanism, are now so accurate that they can detect time dilation effects from walking up a flight of stairs. These ultra-precise clocks are essential for GPS navigation, telecommunications, and fundamental physics research. Future atomic clocks might be accurate enough to detect time dilation effects from moving at walking speed or even from the rotation of the Earth. Such precision would open new possibilities for testing Einstein's theories and searching for new physics beyond our current understanding. The quest to measure time more precisely continues to push the boundaries of technology and our understanding of the universe. Optical atomic clocks, which use laser light to probe atomic transitions, represent the cutting edge of timekeeping technology. These clocks are so stable that they would lose less than 1 second over the age of the universe. They're sensitive enough to detect gravitational time dilation from height differences of just a few centimeters, opening new possibilities for studying Earth's gravitational field and testing fundamental physics. The development of portable optical atomic clocks could revolutionize our ability to study time dilation effects. Imagine carrying an atomic clock on a high-speed aircraft or spacecraft and directly measuring time dilation as it occurs. Such experiments would provide new tests of Einstein's theories and might reveal subtle effects that we haven't yet discovered. Time dilation also affects our understanding of the universe's ultimate fate. As the universe continues to expand and accelerate due to dark energy, distant galaxies will eventually recede from us faster than light due to the expansion of space itself. This creates a cosmic horizon beyond which we can never receive information. The observable universe will shrink over time even as the total universe continues to grow. In the far future, time dilation effects from cosmic expansion might become extreme. Observers in different parts of the universe might experience vastly different rates of time passage. What seems like billions of years to one observer might be mere moments to another. The universe might fragment into causally disconnected regions, each experiencing its own version of time. The study of time dilation has revealed profound connections between seemingly unrelated phenomena across the cosmos. When massive stars collapse into neutron stars, their surfaces can rotate at speeds approaching 20% of light speed. The matter at the equator of these ultra-dense objects experiences significant time dilation compared to matter at the poles. This creates measurable effects in the star's magnetic field and radiation patterns that astronomers can detect from thousands of light-years away. Magnetars, neutron stars with magnetic fields trillions of times stronger than Earth's, provide extreme laboratories for studying time dilation. When these objects undergo starquakes, sudden rearrangements of their crystalline crusts, the resulting energy release can be detected across the galaxy. The time dilation effects near these objects are so extreme that matter falling onto their surfaces experiences time at dramatically different rates depending on its location and velocity. The Fermi Gamma Ray Space Telescope has detected gamma-ray bursts from magnetars in our galaxy and beyond. These brief but incredibly energetic flashes involve matter accelerated to significant fractions of light speed in the intense magnetic field surrounding these objects. The gamma rays we detect carry information about time dilation effects occurring in some of the most extreme environments in the universe. Active galactic nuclei, powered by supermassive black holes consuming matter, create jets of particles traveling at 99% of light speed or faster. These relativistic jets extend for thousands of light years and experience extreme time dilation. Matter in these jets might experience the journey from the black hole to intergalactic space as lasting only years or decades, while outside observers see the process unfold over millions of years. The study of these cosmic jets has revealed how time dilation affects the propagation of information across vast distances. Radio telescopes can track individual features in these jets as they move outward from their source. Due to time dilation and light travel effects, these features sometimes appear to move faster than light, an illusion created by the geometry of observation and the extreme speeds involved. Quasars, the most luminous objects in the universe, are powered by matter falling into supermassive black holes billions of times more massive than our Sun. The accretion disks around these black holes rotate at significant fractions of light speed, creating extreme time dilation effects. Matter spiraling inward experiences time at different rates, depending on its distance from the black hole and its orbital velocity. The Event Horizon Telescope's observations of the supermassive black hole in galaxy M87 revealed matter orbiting at about 30% of light speed near the event horizon. This plasma experiences time dilation factors of several percent, significant enough to affect the dynamics of the accretion flow and the emission of radiation that we observe from Earth. Gravitational lensing, the bending of light by massive objects, creates natural experiments in time dilation. When light from a distant quasar passes near a galaxy on its way to Earth, the galaxy's gravity bends the light and creates multiple images of the same object. Each image follows a different path through curved spacetime, experiencing different amounts of time dilation and gravitational delay. The time delays between these multiple images can be measured with careful monitoring over months or years. When the distant quasar brightens or dims, the change appears in each lensed image at different times. These time delays encode information about the mass distribution of the lensing galaxy and the expansion rate of the universe. They provide an independent way to measure cosmic distances and test our understanding of dark energy. Some gravitational lens systems create spectacular displays where the same distant object appears 4 or more times in a single image. The famous Einstein cross shows a distant quasar lensed by a foreground galaxy into 4 bright images arranged in a cross pattern. Each image shows the quasar at a slightly different time due to the different light paths and time dilation effects, creating a natural time-lapse movie of a distant cosmic event. The Hubble Space Telescope has monitored gravitational lens systems for decades, measuring time delays with precision of days or weeks. These measurements have revealed that the universe is expanding at an accelerating rate, confirming the existence of dark energy. The time delays are sensitive to the geometry of spacetime and the distribution of matter along the line of sight, making them powerful probes of cosmic structure. Binary black hole mergers detected by LIGO and Virgo provide direct observations of extreme time dilation in action. In the final seconds before 2 black holes merge, they spiral around each other at significant fractions of light speed. The gravitational waves they emit carry information about these extreme velocities and the associated time dilation effects. The chirp pattern of gravitational waves, the characteristic increase in frequency and amplitude as the black holes spiral inward, encodes information about how time dilation affects the orbital dynamics. As the black holes accelerate to higher speeds, time dilation becomes more pronounced, affecting the rate at which they lose energy and spiral inward. These effects are measurable in the gravitational wave signals detected on Earth. The merger of 2 neutron stars detected in 2017, designated GW1 70817, provided the first simultaneous observation of gravitational waves and electromagnetic radiation from the same event. The time dilation effects experienced by matter in this merger were extreme, with some material accelerated to speeds approaching light speed during the collision. The electromagnetic counterpart to this gravitational wave event, a kilonova explosion, was observed by telescopes around the world. The light curves and spectra of this explosion encode information about the extreme physics occurring during the merger, including time dilation effects on the radioactive decay of heavy elements created in the collision. Cosmic ray particles provide natural experiments in time dilation on a galactic scale. Ultra-high energy cosmic rays with energies exceeding 10 to the 20th electron volts travel at speeds so close to light that they experience extreme time dilation. From their perspective, crossing the galaxy takes only minutes or hours, while outside observers see journeys lasting tens of thousands of years. The Pierre Auger Observatory in Argentina and the Telescope Array in Utah detect these ultra-high energy cosmic rays when they collide with Earth's atmosphere. The resulting particle showers contain information about the original cosmic rays' energy and composition. Time dilation effects during the cosmic rays' journey through space can affect how these particles interact with the cosmic microwave background radiation, providing clues about their origins. The GZK cutoff, predicted by Kenneth Greisen, Georgy Zatsepin, and Vadim Kuzmin, sets a theoretical limit on the energy of cosmic rays that can reach Earth from distant sources. Protons with energies above this threshold interact with cosmic microwave background photons and lose energy during their journey. Time dilation affects these interactions, influencing how far ultra-high energy cosmic rays can travel before being degraded. The search for violations of Einstein's theories continues with ever-increasing precision, but time dilation effects consistently match theoretical predictions. Tests using atomic clocks on airplanes, satellites, and even tall buildings have confirmed time dilation to extraordinary accuracy. The Gravity probe, a mission in 1976, flew a hydrogen maser atomic clock, to an altitude of 10,000 kilometers, measuring gravitational time dilation with precision better than 1 part in 10,000. Modern tests of time dilation push the boundaries of measurement precision. The Pharaoh mission, part of the Atomic Clock Ensemble in Space Project, will place ultra-stable atomic clocks on the International Space Station to test Einstein's theories with unprecedented accuracy. These experiments could reveal tiny deviations from general relativity that might point toward new physics beyond our current understanding. The development of quantum sensors and atomic interferometry opens new possibilities for testing time dilation. These technologies can measure gravitational effects and accelerations with extraordinary sensitivity, potentially revealing subtle aspects of time dilation that haven't been explored before. Future experiments might detect time dilation effects from the motion of continents or the rotation of the galaxy itself. Time dilation plays a crucial role in our understanding of dark matter and dark energy, the mysterious components that make up 95% of the universe. Dark matter's gravitational effects influence time dilation around galaxy clusters and other massive structures. Precise measurements of time dilation could provide new ways to map dark matter distributions and test alternative theories of gravity. The accelerating expansion of the universe, driven by dark energy, creates time dilation effects on cosmic scales. As space expands, the rate of cosmic time passage changes relative to local time. This cosmological time dilation affects how we observe distant supernovae, galaxy evolution, and other cosmic phenomena. Understanding these effects is crucial for interpreting observations of the distant universe. Proposed space missions could test time dilation in new regimes. The Laser Interferometer space antenna, planned for launch in the 2030s, will detect gravitational waves from space with unprecedented sensitivity. This mission will observe black hole mergers and other events involving extreme time dilation effects, providing new insights into the nature of space-time itself. Future missions to the outer solar system will experience measurable time dilation effects due to their high velocities relative to Earth. The Parker Solar Probe, already the fastest human-made object, will reach speeds exceeding 700,000 kilometers per hour during its closest approaches to the Sun. While still tiny, the time dilation effects will be measurable with atomic clocks and could provide new tests of relativity in the solar system. The concept of time dilation has implications for the search for extraterrestrial intelligence. If alien civilizations exist and travel at high speeds between star systems, they would experience time dilation effects that could affect their development and communication patterns. A civilization that regularly travels at relativistic speeds might experience time very differently from one confined to a single planet. CT researchers consider time dilation when planning searches for alien signals. A message sent from a civilization traveling at high speed would be Doppler shifted and time dilated, affecting its frequency and duration. Advanced civilizations might use these effects deliberately, encoding information in the time dilation patterns of their transmissions. The possibility of time dilation affecting alien biology raises fascinating questions. Would organisms that evolved in high-speed environments experience biological processes differently? Could natural selection favor traits that take advantage of time dilation effects? These speculative questions highlight how time dilation might influence the evolution of intelligence throughout the universe. Artificial intelligence and computer systems face fundamental limits imposed by time dilation. Information cannot be processed faster than light can travel between components, creating bottlenecks in high-speed computing systems. Future quantum computers might exploit time dilation effects to perform certain calculations, using the relative nature of time to their advantage. The development of relativistic computers, systems designed to operate at significant fractions of light speed, remains highly speculative but theoretically possible. Such systems would need to account for time dilation effects in their operation, potentially using these effects to synchronize distributed computations across vast distances. Time dilation affects our understanding of consciousness and the nature of subjective experience. If time is relative, what does this mean for our perception of duration and sequence? Some philosophers argue that consciousness itself might be a relativistic phenomenon, dependent on the observer's reference frame and motion through spacetime. The hard problem of consciousness, explaining how subjective experience arises from physical processes, becomes even more complex when time dilation is considered. If consciousness depends on the timing of neural processes, how would extreme time dilation affect subjective experience? These questions remain largely unexplored, but could become relevant as we develop technologies for high-speed space travel. Virtual reality and simulation technologies might someday allow us to experience time dilation effects without actually traveling at high speeds. By carefully controlling the timing of sensory inputs and neural stimulation, it might be possible to create the subjective experience of time dilation. Such technologies could help prepare astronauts for the psychological effects of relativistic travel. The study of time dilation has revealed the deep interconnectedness of space, time, matter, and energy. These aren't separate entities, but aspects of a unified reality that we're only beginning to understand. Every measurement of time dilation provides new insights into the fundamental nature of existence itself. Educational approaches to teaching time dilation continue to evolve as we develop better ways to visualize and understand these counterintuitive effects. Interactive simulations, virtual reality experiences, and hands-on experiments with atomic clocks help students grasp concepts that once seemed purely abstract. Understanding time dilation is becoming essential scientific literacy in our increasingly technological world. The cultural impact of time dilation extends beyond science into art, literature, and philosophy. Artists have created works inspired by the malleability of time, writers have explored the human drama of relativistic travel, and philosophers have grappled with the implications for free will and determinism. Time dilation has become part of our collective understanding of reality. Time dilation research continues to drive technological innovation. The need for precise timekeeping has led to advances in atomic clocks, laser technology, and quantum sensors. These technologies find applications far beyond fundamental physics, from telecommunications to navigation to financial trading systems that require precise time synchronization. The economic implications of time dilation become significant as we consider future space commerce and interstellar trade. Imagine a cargo ship traveling between star systems at 80% light speed. The crew might experience a 5-year journey while decades pass on their homeworlds. By the time they return, markets could have completely changed, currencies might have been replaced, and the goods they're carrying could be obsolete. Time dilation creates unique challenges for any economy that spans multiple star systems. Financial systems would need to account for time dilation effects in interstellar transactions. How do you calculate interest rates when time itself is relative? What happens to contracts and agreements when the parties experience time at different rates? These aren't just theoretical problems, they're practical challenges that future spacefaring civilizations will need to solve. Insurance companies would face unprecedented challenges in a relativistic economy. How do you assess risk when time dilation affects the duration of journeys and the aging of equipment? A spacecraft traveling at 90% light speed might experience only 1 year of wear and tear during what appears to be a 10-year journey to outside observers. Traditional actuarial models would need complete revision. The legal implications of time dilation are equally complex. If a crime is committed on a spacecraft traveling at relativistic speeds, in which jurisdiction should it be prosecuted? How do you determine the statute of limitations when time itself is relative? Legal systems would need new frameworks to handle cases involving time dilation effects. Communication networks spanning multiple star systems would need to account for time dilation in their protocols. Messages sent between worlds moving at different velocities would experience time dilation effects that could affect their timing and synchronization. Future Internet protocols might need to include relativistic corrections to maintain coherent communication across vast distances. The psychological effects of time dilation on human relationships remain largely unexplored. Imagine maintaining a friendship or romantic relationship when one person regularly travels at relativistic speeds. The time-dilated traveler would age more slowly, creating an ever-widening gap in their shared experiences. These effects could fundamentally change how we think about human connections and social bonds. Family structures might evolve in response to time dilation effects. In a society where some members regularly travel at high speeds, traditional concepts of generations and aging would become fluid. Parents might find themselves younger than their children, and siblings could age at different rates depending on their career choices and travel patterns. Educational systems would need to adapt to time dilation effects. How do you maintain academic standards when students might experience education at different rates due to time dilation? A student traveling at relativistic speeds might complete years of study in what appears to be months to outside observers. Standardizing education across a relativistic civilization would require entirely new approaches. Medical practice would face unique challenges in treating patients who have experienced significant time dilation. Biological aging might not correspond to chronological age, making diagnosis and treatment more complex. Medical records would need to account for both proper time, experienced by the patient, and coordinate time, measured by outside observers. The development of life extension technologies could interact with time dilation in unexpected ways. If medical advances allow humans to live for centuries, time dilation effects during space travel could become even more significant. A person who lives for 500 years might spend decades of that time traveling at relativistic speeds, experiencing complex interactions between biological aging and time dilation. Archaeological and historical research would be transformed by time dilation effects. Artifacts and records from relativistic travelers would need to be dated using both their creation time and the time dilation they experienced. Historical timelines would become multidimensional, accounting for the different temporal experiences of various groups and individuals. The preservation of culture and knowledge across time-dilated civilizations presents unique challenges. How do you maintain cultural continuity when different groups experience time at different rates? Languages, customs, and traditions might evolve at different speeds, creating divergent branches of human culture, separated not just by space, but by time itself. Religious and philosophical traditions would need to grapple with the implications of time dilation for concepts of eternity, mortality, and spiritual development. If time is relative, what does this mean for beliefs about afterlife, reincarnation, or spiritual progress? Different religious communities might develop vastly different interpretations of time dilation's significance. The arts would likely flourish in new directions as artists explore the creative possibilities of time dilation. Musicians might compose pieces that unfold differently depending on the listener's reference frame. Visual artists could create works that change based on the observer's motion through space-time. Literature might develop new narrative techniques to capture the experience of relativistic travel. Sports and competitive activities would need new rules and categories to account for time dilation effects. How do you fairly compare athletic performances when competitors might have trained under different time dilation conditions? Olympic records might need separate categories for Earth-based and space-based achievements. The concept of simultaneity becomes crucial for coordinating activities across a relativistic civilization. Without a universal now, scheduling meetings, coordinating projects, and synchronizing activities becomes incredibly complex. New social protocols would need to emerge to handle the practical challenges of relative simultaneity. Time dilation effects could influence the evolution of human consciousness itself. If groups of humans regularly experience time at different rates, might this lead to different ways of thinking about causality, memory, and planning? The human brain evolved in a world where time seemed absolute. How might it adapt to a relativistic reality? The study of time dilation continues to reveal new aspects of reality that challenge our understanding. Recent research into quantum gravity suggests that time itself might be quantized at the smallest scales, made up of discrete units rather than flowing continuously. Such discoveries could revolutionize our understanding of time dilation and its fundamental nature. Emerging technologies like quantum computers and artificial intelligence might provide new tools for studying and exploiting time dilation effects. Quantum systems naturally exist in superpositions of different states, potentially allowing them to explore multiple temporal paths simultaneously. AI systems might develop intuitive understanding of relativistic effects that humans find counterintuitive. The search for a theory of everything, a unified description of all fundamental forces, necessarily involves understanding time dilation at the deepest level. String theory, loop quantum gravity, and other approaches to quantum gravity all make predictions about how time dilation behaves under extreme conditions. Testing these theories requires pushing our understanding of time dilation to new limits. The intersection of time dilation with quantum mechanics creates some of the most puzzling questions in modern physics. Quantum entanglement seems to allow instantaneous correlations between particles regardless of distance, yet no information can travel faster than light. How do time dilation effects influence quantum entanglement? If two entangled particles are separated and one experiences extreme time dilation, does this affect their quantum connection? Recent experiments have begun to explore these questions using atomic clocks and quantum systems. Scientists have created entangled atomic clocks and subjected them to different gravitational fields to study how time dilation affects quantum correlations. These experiments probe the boundary between quantum mechanics and general relativity, potentially revealing new physics at the intersection of these fundamental theories. The concept of quantum time dilation suggests that time itself might be subject to quantum uncertainty. Just as particles can exist in superpositions of different positions or energies, they might exist in superpositions of different temporal states. This could mean that time dilation effects are fundamentally probabilistic rather than deterministic, adding another layer of complexity to our understanding of spacetime. Decoherence, the process by which quantum systems lose their quantum properties through interaction with their environment, might be affected by time dilation. If quantum coherence times are measured differently in different reference frames, this could have implications for quantum computing and quantum communication systems operating in relativistic environments. The development of relativistic quantum information theory attempts to understand how quantum information behaves in the presence of time dilation and curved spacetime. This emerging field could lead to new technologies that exploit both quantum mechanics and relativity, potentially enabling quantum communication networks that span interplanetary or even interstellar distances. Time dilation effects in biological systems remain largely unexplored territory. While we understand how time dilation affects physical processes, we don't fully understand its implications for living organisms. Would cellular metabolism slow down proportionally with time dilation? How would circadian rhythms adapt to relativistic travel? These questions become crucial as we plan for long-duration space missions at high speeds. The study of extremophiles, organisms that thrive in extreme environments, might provide insights into how life could adapt to time dilation effects. Some bacteria can survive in conditions of extreme radiation, temperature, and pressure. Understanding their survival mechanisms might help us predict how life could adapt to the extreme conditions associated with relativistic travel. Genetic expression and DNA repair mechanisms might be affected by time dilation in ways we don't yet understand. If the rate of molecular processes changes with time dilation, this could affect how genes are expressed and how cells repair damage. Future space missions might need to monitor these effects carefully to ensure crew health during relativistic journeys. The psychological adaptation to time dilation presents unique challenges for human space exploration. How do you maintain mental health when your perception of time becomes disconnected from the rest of humanity? Astronauts on relativistic missions might need entirely new forms of psychological support and training to cope with the temporal isolation. Virtual reality technologies might help astronauts maintain connections with Earth-based time during relativistic journeys. By simulating Earth normal time flow in virtual environments, crew members might be able to maintain psychological anchors to their home world's temporal experience. These technologies could become essential for maintaining crew mental health on long-duration, relativistic missions. The development of artificial gravity through rotation could interact with time dilation in complex ways. A rotating spacecraft creates artificial gravity through centrifugal force, but different parts of the ship move at different speeds. This could create subtle time dilation gradients within the spacecraft, with crew members at different locations experiencing slightly different rates of time passage. Time dilation effects could influence the design of future spacecraft and space habitats. Engineers would need to consider how time dilation affects the aging of materials, the operation of electronic systems, and the synchronization of onboard computers. Spacecraft designed for relativistic travel might need entirely new approaches to systems integration and maintenance. The concept of proper time, the time experienced by an object in its own reference frame, becomes crucial for understanding biological and psychological processes during relativistic travel. While outside observers might see a journey lasting decades, the travelers experience only their proper time. This distinction becomes essential for planning missions and understanding their effects on crew members. Navigation systems for relativistic spacecraft would need to account for time dilation effects in their calculations. GPS-style systems wouldn't work across interstellar distances, and new approaches to navigation would be needed. These systems would need to account for the time dilation experienced by both the spacecraft and any navigation beacons or reference points. The study of time dilation has implications for our understanding of aging and longevity. If time dilation can effectively slow biological aging relative to outside observers, this might provide insights into the fundamental nature of aging itself. Understanding how time dilation affects biological processes could lead to new approaches to life extension and age-related disease prevention. Chronobiology, the study of biological rhythms and their relationship to time, would need to expand to include relativistic effects. How do circadian rhythms adapt to time dilation? Do biological clocks continue to function normally in time-dilated reference frames? These questions could become crucial for maintaining crew health during relativistic space missions. The social implications of time dilation extend beyond individual psychology to entire communities and civilizations. How do you maintain social cohesion when different groups experience time at different rates? Future spacefaring societies might develop entirely new social structures and institutions to handle the challenges of relativistic existence. Communication protocols for relativistic civilizations would need to account for time dilation effects in message transmission and reception. Standard communication methods assume synchronized time between sender and receiver, but time dilation makes this assumption invalid. New protocols would need to handle messages that arrive at different rates, depending on the relative motion of communicating parties. The preservation of historical records becomes complex in a relativistic civilization. Events that occur simultaneously in one reference frame might appear to happen at different times in another. Historical timelines would need to account for multiple temporal perspectives, creating multidimensional records of past events. Educational curricula would need to include relativistic literacy as a basic skill. Understanding time dilation and its effects would become as fundamental as understanding basic mathematics or reading. Students would need to develop intuitive understanding of relativistic effects to function effectively in a spacefaring civilization. The economic modeling of relativistic societies presents unprecedented challenges. Traditional economic theories assume synchronized time and simultaneous transactions. In a relativistic economy, supply and demand could be affected by time dilation effects, creating new forms of market dynamics and economic relationships. Time dilation also reveals the profound interconnectedness of all things in the universe. The same physical laws that govern the behavior of subatomic particles also determine how time flows for galaxies billions of light-years away. From the smallest quantum fluctuations to the largest cosmic structures, everything is connected by the fundamental principles of spacetime and relativity. This interconnectedness should inspire both humility and wonder. We are part of a universe that is far stranger and more beautiful than our everyday experience suggests. Time itself is not the constant, unchanging backdrop we once thought it was, but a dynamic, flexible dimension that responds to motion and gravity in ways that still challenge our intuition. The search for a complete understanding of time dilation continues to drive scientific research and technological development. Quantum gravity theories attempt to unify Einstein's relativity with quantum mechanics, potentially revealing new aspects of time dilation at the smallest scales. These theories might show that time itself is quantized, made up of discrete units rather than flowing continuously. Future experiments with atomic clocks, gravitational wave detectors, and particle accelerators will continue to test our understanding of time dilation with ever-increasing precision. Each new measurement provides another piece of the puzzle, helping us understand how time, space, matter, and energy are woven together into the fabric of reality. The study of time dilation also reminds us that science is a collaborative human endeavor that spans generations and cultures. Einstein's insights built on the work of earlier scientists like Lorentz and Poincaré. Modern experiments confirming time dilation involve thousands of researchers from around the world working together to push the boundaries of human knowledge. This collaborative spirit is essential as we face the challenges of becoming a spacefaring civilization. Understanding time dilation is just one piece of the puzzle. We also need to develop new technologies, solve engineering challenges, and address the social and psychological aspects of relativistic travel. These challenges require the combined efforts of scientists, engineers, philosophers, and dreamers from all walks of life. As you look up at the night sky, remember that you're seeing a universe where time itself is relative and malleable. The light from those distant stars has been traveling for years, decades, or even millions of years to reach your eyes. You're literally seeing the past, preserved in photons that have journeyed across the cosmos at the ultimate speed limit. But you're not just an observer of this cosmic drama, you're a participant in it. Every moment of your life, you're moving through space-time, experiencing time dilation effects that are tiny but real. Your GPS navigation system accounts for these effects. The atomic clocks that synchronize our global communication networks measure them. You live in a relativistic universe, whether you realize it or not. The story of time dilation is ultimately a story about the power of human curiosity and imagination. Einstein's insights came not from expensive equipment or massive laboratories, but from thought experiments and mathematical reasoning. He imagined what it would be like to ride alongside a beam of light, and from that simple question, he revolutionized our understanding of space and time. This reminds us that the next great breakthrough in our understanding of time dilation might come from anyone, anywhere. It might come from a student puzzling over the equations of relativity, an engineer designing spacecraft for interstellar missions, or a philosopher contemplating the nature of time itself. The universe is full of mysteries waiting to be discovered, and time dilation is just one of them. And have you ever wondered how far we can travel in space? In this VIDE at the left side of the screen, we will discover the farthest humans have ever traveled. We examine Mars colonization timelines, asteroid mining economics, space elevator construction, the search for habitable exoplanets, and much more. See you there.